We've got rules for limits that are easily proved if you do the epsilons and deltas on a general function. I'm not going to go into the proof. I don't think your book goes into the proof. It simply states it, and it says it's pretty easy to prove these things. And it really is pretty easy to prove it in 5 minutes or less. But anyhow, the limit of f of x plus g of x is a limit of f of x plus the limit of g of x. Not a rigorous statement. I'd have to say the limit as x goes to a of f of x plus g of x is the limit as x goes to a of f of x plus the limit as x goes to a of g of x. But basically, the limit of the sum is the sum of the limits. A sum of functions. Now, I can make the same statement. The limit of a multiple is a multiple of limits. Trying to write short and leaving letters out, okay? So if you got a function f of x times g of x, you just multiply the two limits. Now that assumes that both limits exist. If they don't both exist, you can't add them, right? You can't add something that doesn't exist to something that does. Get one non-existence and you got the whole thing is non-existent. Now you can read this in your book, and you should, because the book makes the full statement of each of these things. I'm not going to write out the full statement. The idea is so simple that I'm just going to write it in simple form. But make sure you look at the statement and understand all the words and conditions. Statements aren't much longer than what I'm writing, but see, the board's only this wide. Yeah. Okay. Limit. Limit of quotient is a quotient of limits. But you do want to include the caveat that you better not try it if the divisor has a limit of 0. Because then when you try to do the quotient of the limits, you get something over 0. Then you got to be a little bit careful. The limit of a composite function is a composite of the limits. Wait a minute, I didn't say that right, but we'll apply it in a minute. Okay, let's see how these apply. This really isn't quite true. So I'll just kind of cross this out for a moment and fix it. Okay, so for example, the limit of 1 over x squared plus y squared that I just did in terms of epsilons and deltas, that limit is limit is x, y goes to 1, 1 of 1. Well, 1 is always 1. It doesn't change, so its limit is 1. And I should have put the x, y goes to 1, 1 as a subscript here, but I think you understand what I'm trying to write. And this equals 1 over the limit as x, y goes to 1 of x squared plus the limit of y squared. So you can break this down. You don't even, y has no effect on the limit of x squared. It's real easy to prove that the limit of x squared as x approaches 1 is 1. You can use epsilons and deltas, and you don't have to worry about the geometry of a circle and that straight line. It ensures that x plus y is less than 2 plus delta. Okay? And same thing for y squared. Okay, I crossed out the word composite. We'll deal with composites and we'll do an example of the composite, make sense of it, because it's the only one that isn't completely obvious. Again, I got in a pattern of writing stuff out. That's something I shouldn't have, but it applies for any exponent, any power. And I need that now, because I want to say that the limit of x squared is the square of the limit of x. Since y is not involved in the limit of x squared, I don't have to include the fact that y goes to 1. Doesn't make any difference. So the limit of x squared is the square of the limit of x. Now that's totally obvious that that's got to be 1. Although it wouldn't be hard to prove at all. The epsilons and deltas would be very simple. Now all of a sudden, no, I don't think I did. Suddenly seems like I did something really boneheaded. Got an email from an old cousin, actually a second cousin. His mom is my mom's cousin. But we family, we kind of alternate going to their house or them coming to our house for Christmas. Not on Christmas Day, but the day after Christmas. And we saw them a couple of times a year. Their son's my age. Actually, he's a year older than I am for 3 months out of the year, I think. He's wanting to get together. I haven't seen him in years. And he and his wife are doing a bike ride in North Carolina, so they're going to come down and want to stop by and visit, just have dinner or something before they go into North Carolina. And but anyhow, he said they're going to be, the bike ride, they register on the 4th, and bike ride is 5th, I guess, of November. So we want to get together on the 3rd. But just the way the email was written, I picked up the 4th, so I said, okay, 4th is good. I'll make a dinner reservation. Okay. And then I got to thinking about it. I thought, walking up down hills for a little while to calm myself down. And actually just try to keep my legs in shape. But I thought, wait a minute. He's doing this ride, registering the 4th, he's going to want to be here on the 3rd. I went back and saw the 3rd on the email. So had to email him back and said, oh, yeah, it's the 3rd. That's fine too. So I do bonehead things like that. And you see me do it at least an average of 80 times a day. So maybe I've done something. I don't think I did. Check back on what I did and make sure. Okay, you see how these rules can be helpful. This is a lot easier than what we did there. Of course, it depends on being able to prove that what we did there kind of always works. All right. Now I want to go ahead and, so we've used, what have we used? We've used the rule for the quotient. We've used the rule for power. And we've used the rule for a sum. Because we took this limit and made it into sum of limits. Then we took each of these and made it into a power of limits. And of course we took the original expression, made it into quotient of limits. It's always safe to do that. Okay, we're going to talk about an example of a composite, and it's fairly straightforward.